Hello and welcome to our poster titled Strain Sensing Using Colloidal Quantum Dots Integrated with Epoxy for the IEEE Sensors 2020 conference. My name is Michael Sherburne and my co-authors are Candice Mueller, John Brewer Jr., Thomas Weber, Todd Laurvick, and Hengky Chandrahalim. And our work is about addressing a need for better optical strain diagnostics using nanotechnology, specifically using a material called colloidal quantum dots, the same material used in your high-end TV displays. And we are utilizing their strain sensing properties, as can be seen here with this energy and momentum diagram. When a colloidal quantum dot is strained, either tensile or compressive, it will change its band gap, which changing the band gap will change the emission wavelength that it will emit when it is excited. And we can apply this within a polymer as a paint onto a pre-coated structure. And what's important here is this epoxy pre-coating that we've used, which is made by Solvay. And you can see here on this 3D surface map that we have the CQD loaded or colloidal quantum dot loaded polymer that's applied on the left and the pre-coating on the right. And what's cool is the colloidal quantum dot loaded polymer will actually just go right into all the rough surfaces of the pre-coating, which is useful for adhesion in realistic applications such as aeronautics. This is our experimental setup. It's really simple. We just use a black light to excite the colloidal quantum dot thin film here, and then the emission from the colloidal quantum dots will go to a collimator while the sample is going under tensile strain, and then this is collected by the spectrometer. And then looking at the wavelengths from the spectrometer, you can see over strain that the emission spectra changes over time. And we can use some empirical formulas to go ahead and then calibrate the emission wavelengths that are here in terms of their relative photoluminescence intensities, and we can compare this to the mechanical stress strain curve and then shift it accordingly in order to get a calibration from this optical data. And what's really important is this epoxy peak, which can be used as a reference anchor point in order to help with the calibration process. At the end of it, you can get this beautiful stress strain curve here, comparing the optical to the mechanical, and it follows it very closely all the way till the end, which is failure. And the reason for all the deviation on the left side here is because the film is not over the entire dog bone itself, it's actually in a local area. Thus, it's going to be looking at a localized strain, not the overall that the mechanical can do. And the possibilities are endless for the future use of this technology. For example, the most near-term use could be in quality assurance, where you can look at components that are critical for different types of infrastructures or for whatever, and by having the paint on it while you're testing the component under strain, you can actually get a 2D strain surface map with a feature camera with a lasering rastering system. And that could be easy to use by the operator. Thank you for listening to our poster. Please let us know if you have any questions.